All right, we're going to start a new chapter. Finally, we got out of chapter 12. We're going to jump to chapter 14, which deals with reaction rates, how quickly a chemical reaction goes. Now, a rate is anything that is a comparison of two values, usually with time. So like in a car, you look at miles per hour. So you're comparing miles with hours, distance with time. Well, it's kind of hard to do that in chemistry with distance, but we can look in terms of how much of the reactants are used up or how much of the products are created over a certain period of time. That is the definition of a reaction rate. Now, hopefully you've seen this video. If not, you need to stop at this point and watch this video before I go any farther. Go ahead and do that if you haven't already. Okay, so let's move on here. Since this is chemistry, the examples they gave in the video is that a slow rated reaction would be the rusting of a car. It takes a long time for the rust to occur. A fast one was the dropping of magnesium into the hydrochloric acid and the bubbles start appearing. And it's not very quick, but it's quick enough you can see the bubbles created. So you actually see the products occurring. You won't be able to see the hydrochloric acid disappear unless you had some kind of pH meter, which you would then. But you do see a reaction taking place. And the fast one would be any explosion is a violently, super quick reaction where things happen instantaneously as soon as the explosion occurs. Now, there's a graph on your page, in your book on page 592 that shows oxygen being created in a particular chemical equation. Now, the graph for that particular one looks something like this. Starts here, and then does this kind of thing right here. And so it starts at the origin right here, where there was no oxygen at all. In that particular graph, we're dealing with moles of oxygen with time. And as you can see, the slope is going up pretty quick. And then as you go over here, it gets smaller and smaller, which means the rate of reaction decreases over time. Meaning, you get lots of it here and not so much of it here. And the reason for that being is that as the molecules are created, you're creating more molecules in a way of a reaction to occur. Now, how does a reaction occur? It occurs by collisions. So if you have what other particles are reacting with oxygen in this particular reaction, and you're throwing in oxygen as a result of that reaction, then the oxygen molecules created start to get in the way. So when the other particles are trying to collide to create this oxygen, the oxygen that has been created at this point starts blocking it. And so it slows it down to the point where it's actually going to taper off into a horizontal line, which means we have run out of reactants. And so no more oxygen can be produced. The next graph on page 593 is the same kind of graph, only now instead of dealing with moles of oxygen, it's dealing with moles per liter of oxygen, and they call that the concentration of oxygen in moles per liter. Now, these brackets right here mean concentration. And the choice of concentration is moles per liter when we're dealing with aqueous solutions. Gases, a lot of time we use mole fraction or molality, but in liquids, liquid reactions, and this is a liquid reaction, even though the product is a gas, true, but it was the result of aqueous solutions reacting together. So this is a liquid reaction, so they use moles per liter. And we can use moles per liter for gases as well, anyway. But because this is being run in a water reaction, they will always use moles per liter for it. Okay? So, you take a look at, there's a problem page 595 towards the bottom page. And they give you a graph of what it looks like when you focus on the reactants instead of the products being created, the reactants, what they call decomposing, going away. So that thing looks like this. Then like so. No, whatever. Okay, so now we're going to have concentration of a substance. I'll call A and time here. And you're starting with a certain concentration of your reactants. And let's say the reaction here is A yields B. Okay, something very generic. And so this is going to be exactly opposite. It start off decomposing quickly because there's nothing getting in the way of it. The A particles reacting or colliding with each other. But as more and more B particles get produced, it's going to get in the way. So it's going to look something like this. And again, if we take a look at the slope at each particular point on this, of the tangent of each point on here, you'll notice that you're getting this kind of change in slope with time, and you can see it's starting to level out over here, where it's going to either go to zero, or it's just going to maintain a what we call an equilibrium condition, where it's not going to change. So, and that depends upon what's going on with the other substances. So if we focus only on the reactant, it's exactly the same as the other, only it's in the opposite direction. So start a lot, quick drop, slowly changing, and not so negative to the point where it approaches zero. And to refresh your memory, the other one looked like this. We could consider that what B is. This is the concentration B for this as it goes up. And you see their options. Okay? So one is decomposing, the other is forming. So we call one a rate, the speed at which this occurs, the rate of decomposition, and the rate of formation. Okay? So it says, here's an example. In a reaction, a compound HCl decomposes into H2 and Cl2. The initial concentration before the reaction starts is 0.35 mole. And we're talking about is the HCl, because we're focusing on the reactants and not the products. After the reaction is run for 15 minutes, the concentration of HCl becomes 0.188 moles per liter. And what is the average rate of reaction? Okay, now, first you need to change the 15 minutes into seconds. Why? Because it asks for the rate but it doesn't say here, well, I'll have it fixed for you in there, but they're looking for the change of concentration or the decomposition in moles per liter per second. So I'll make sure to get that put in there for your script when we get to that point. Okay, so, oops, go back down here. So we go back over here to the problem. And so we have to change the 15 minutes into seconds, or 60 seconds in a minute, so that gives you 900 seconds. If a reaction decomposes, that means that the amount is going to get smaller and smaller, so that's going to give you a negative value for the change. Now, delta again means change, which means final minus beginning. So when we find the rate, we're going to, because this is decomposition, we start off with a negative sign, and this is going to be 0.188 is the final. That's the final. It's going to end up there. And it starts at 0.35 moles per liter. That's your numerator, and your subtraction of it. Your denominator, you end up at 900 seconds, you start at 0 seconds. So that's your delta T. And you divide that out, and you get 1.80 times 10 to the negative 4. That should be the next one, negative 4 moles per liter per second. Again, I'll fix that in the script before we get to that point, where we have to look at. Another example, rate of formation in moles per liter of the Cu2O. So now this is going to be a positive now. We're looking from the product's point of view. So it starts at 0 and goes up. So now your initial is 0, and your final is 1.28 moles per liter. This is a fairly slow reaction, so it takes 2 hours to get to this point. So we got to change the 2 hours into seconds, and that gives you 7,200 seconds. The rate is the final 1.28 minus the initial 0 moles per liter divided by the change in time. We end up at 7,200 seconds, start at 0, and we get 1.78 times 10 to the negative 4 moles per liter per second. All right, practice problems, page 640, problems 35 through 38 all. Good luck.